All right, so yesterday I posted the majority of the questions from Practice Exam B up on our YouTube page. This one just has the rest of the problems we didn't work through on Practice Exam A on Monday. So let's go here. Where are we at? Practice Exam A. So I'm going to go back. I'm going to go over some of these Bayes theorem problems. Okay. Let me make sure I'm recording this. There we go. All right. So we've got this problem. We're given a bunch of information for 10, 11, and 12. So, eventually we're going to have to use Bayes' theorem, but some of the other questions, we may not have to use it yet, but we can use parts of what we're given here to answer problems 10 and 11. So the way I would kind of approach these is just start writing out everything that we know, okay? So suppose that given that someone is lying, probably the lie detector test says they're lying is 90%. So I'm going to pull this up here. So we can kind of see the Word doc as well as what I'm going to be working on here in just a second. Switch this over to our webcam or our doc cam. Might take a moment for it to show up here. So I'll give a momentary pause. Okay, perfect. So you wouldn't have to always do this, right? Light this up a little bit. There we go. But I'm going to work through this as though I could ask you any question about the information given. So I'm going to write down even more than you would have to do maybe for some of these questions. But if I had asked slightly different questions, I'll show you the way in which you can answer any of them, right? So the first thing we're told is suppose given that someone is lying. So anytime we see this word given, right, let's think about that given, right, that someone is, wait, is this lying? Or do I feel like that's spelled wrong? Lying? It can't be right. With a Y, for sure. Not an English major, right? So given that someone is lying, right, the probability the lie detector test says they're lying is 90%. So lie detector says that they're lying is 90%, or probability of 0.9. Okay? So it's the very first thing we were given. Then it says, however, given that an individual is not lying, so given that somebody is not lying, the probability that the lie detector test determines they're lying is 20% of the time, or a probability of 0.2. Okay? So this is just directly what we were given. And then suppose that recent studies found that on average, people lie. So we'll kind of say this as probably they're lying. What, 5% of the time, or 0.05. Okay? So that was just what we were given initially. Right? Now, in any problem, we can use these probabilities to find three other probabilities. Right? So the easiest one is probably, if the probability someone is lying is 0.05, the probability that they're not lying, right, there's only two things you can be doing, lying or not lying. So those have to add up to 1. So if we know the probability of, right, we can think about this as A, the probability of A complement, right, would just whatever gets us up to 1. Okay? The other things that we could determine, and this might be a little bit less clear, given that someone is lying, we know that the lie detector will show they're lying 90% of the time, which means that if we're looking at those same people who are lying, so we still condition on that same state of nature, the probability of the other outcome of the test, not lying, has to be, right, it's the only other outcome we can see for the test, so those two probabilities have to add up to 1. So if this one's 0.9, the other one would have to be 0.1. Okay? And then similarly, if we condition on the other state of nature, so that they are, given that they're not lying, the probability the lie detector test says they're not lying, well, given that they weren't lying, the lie detector incorrectly said they were 20% of the time, or probably 0.2. So the remaining, right, to get us up to 1 would be the other outcome of the test. So the probability they're not lying would just have to be 0.8. Okay. So I can get these all on the screen here. There we go. So we may not need all these probabilities that I just kind of showed you how you could find, But if we did, I'm making sure that you know how you would do that. Okay? Any questions on that? Okay with that? Okay. So now let's start working through these problems, right? And I'll kind of have this on the side. I'll pull it up again if you need to kind of write those down again. You know, if you're watching this video, you could pause it. But for those of you who are here today, I'll be showing this again briefly. Okay. So question 10, I would always kind of approach these, just write out what you're looking for. So that question 10 is the probability that a person is lying, and the lie detector test says they're telling the truth or not lying, right? So what we're looking for here is the probability that somebody is lying, and, right, the lie detector test says they're telling the truth, so not lying. Right? Because when we see a lie detector test saying that someone's not lying, well, there were some people that just slipped through the cracks, right? Some people who actually were lying, but the lie detector test didn't pick it up, right? Because this wasn't a 100% fail-safe test. So anytime we want to find the intersection of two events, we'll go to our formula sheet, scroll up. We've got this equation here, which is anytime we have the intersection of two events, we can rewrite that as the conditional probability times what we're conditioning on. So if we want to think about it as here is our A and here's our B, we can find the intersection by what? Taking the conditional probability of B, right? B given A is what that formula says right here. So the probability the lie detector says they're not lying, given A, our A is given that they're lying, and then multiply that by the probability of what we conditioned on, which was that the individual was in fact lying. Okay? Now from here, it's just a matter of plugging our values in, right? Because we already determined these things earlier. So if we look back, well, it's not here, so we got to go all the way down here, so I have to cover this up for a second. But given that someone's lying, the probability the lie detector test said they weren't lying was 0.1. So we have that conditional probability, plug it in as 0.1. What's the probability that someone's lying? Well, that was just 0.05. So this should just be 0.005. Go back. Sure enough, that's answer A there. Okay. So all we did is once we had it written out, it was just a matter of identifying those things from what we originally had done and plugging those values in. Okay. Any question on that one before we kind of keep moving here? So then on 11, what's the probability that somebody is not lying and the test says they're not lying? Okay. So it's going to be a very similar problem. So now it's, what's the probability that somebody is what? Not lying. And, right, the test says that they're not lying. Okay. So once again, we can kind of think about this is our A, and this is our value for B. Right. Make sure I just had an email to make sure it's not about the link. Okay. So similar idea. We go back to that formula sheet. If I want to find the intersection of two events, I can use the conditional probability times what I'm conditioning on. So this is the same thing as event B. So that was that the lie detector said that they're not lying. Given our event A, which is what that they are not lying, and then multiplied by the probability that they, or whatever we're conditioning on, for that event A, which was that they are not lying. Okay. So we've got it written out in the context of our example. So given that someone was lying, given that someone was not lying, the probability the lie detector said they weren't lying was 0.8. So just plug that value in here. Multiply that by the probability somebody wasn't lying, which we determined earlier was 0.95. So if we do that, well, we're going to get should be able to do this off the top of my head, but I can't. Oops. 0.76. Okay. So those two problems, we really worked them out the exact same way. They're just asking for slightly different probability, right? Slightly different things. But it's really the same procedure and the same formula here was used in either one of them. Okay. So what we get 0.76 here. Oops. I can highlight this. There we go. Any questions on those two? Those ones shouldn't be too bad. The next one's going to be a little bit more difficult. Right? The next one says, given that an individual fails the lie detector test, or basically it's saying that they're lying. So right away, what we're going to write out is, given that the lie detector test shows that someone is lying, right? That's kind of what we're told there. Then what's the probability the individual is actually telling the truth? So what's the probability that they're actually not lying here? Right? And I'm just writing not lying instead of truth just so we kind of keep it consistent with what we did earlier. Right? It's really just two different ways of saying the same thing. Well, if I go to my formula sheet, I might think that, okay, I'm looking for a conditional probability. I can rewrite this as the intersection divided by what I condition on. Now, the problem is if I think about what am I conditioning on here, it's the probability that the lie detector test shows someone's lying. And if I look at my original kind of probabilities, I don't have that, right? So anytime, you kind of notice the practice exams are following a similar format. And a lot of times, anytime you're asked for this conditional probability, if you're not using a contingency table, it's probably going to be that this equation, right, we don't have the probabilities to be able to use it. But if we broke them down, we would eventually arrive at this Bayes theorem equation. And we can use that and just write it out in the context of our example. And then it's probably from there, it's just plugging in probabilities that we had from earlier. Okay? So I'm going to write this out in the context of my example where this is my this is my S, and this is my E. I was thinking one step ahead. Okay, so the probability of S would be the probability that someone is not lying times the probability of E given S. So E was that the lie detector shows lying, given my S, which is that they are not lying. Right? Let me zoom in a little bit on this because I know this red mark is a little bit harder. Oh, I'm going the wrong way. There we go. Okay. I then have to divide that by, well, now notice the very first part of my numerator is first part of my denominator is the same as my numerator. So, in the sake of not running out of room here, you could write this out again, but it's the exact same thing that we have up here in my numerator. So I'm just going to kind of remember that. Now, in practice, when you're doing this, I would write that out again. It's just here, I'm going to run out of room pretty quickly, and I don't want things to kind of look like a mess. I think this will help keep the second part more clear. So we've got that first part of our denominator. Then we add the probability of S complement. So our S is that they're not lying. So our S complement would be that they actually are lying. Multiplied by the probability of E given S complement. So our E is the lie detector test shows they're lying, given S complement, which we just said, if S is not lying, S complement is that they are lying. Okay. Now from here, it's just a matter of plugging things into our equation. So what was the probability that someone wasn't lying? That was 0.95. So 0.95 multiplied by, given that someone's not lying, what's the probability the lie detector test shows they're lying? We had that up here, which was 0.2. Plug that in. Now remember that first part of our denominator was the exact same as up here. Okay. What's the probability someone is lying? We had that earlier. was 0.05. 0.05. Times, given that they're lying, what's the probability the lie detector test shows they're lying? So given that they're lying, the probability the lie detector test shows they're lying was 0.9, right? And now it's just a little bit of math, right? So now we just have to make sure we get this entered into our calculator correctly. And we get about 0.81 approximately, if I round that to the second decimal. Okay, so we go back here. Oh, I didn't round, I had it out to the third decimal here, sorry. We rounded to the third decimal, 0.809. Okay? I should have looked at those answers. Like I mentioned on Monday, whatever decimal the answers have, that's the decimal point you should be rounding to. Okay? Any questions on that? This is probably one of the more difficult questions on the exam. And you kind of notice we actually didn't use these probabilities in 12. We actually only used kind of the ones we were given, I guess, plus we had to kind of know how to find the probability of not lying there. But once we identified all the probabilities that we were given, and then write down what you're looking for, the conditional probability you're looking for, use that along with your formula sheet, right? So you can kind of identify what your S and your E are. And then it's just a matter of writing it out in the context of your example, and then it should just be plugging in those probabilities. So those are the kind of steps to take there. All right. Any questions before we keep moving on that? All right. So the next one we'll work through here is question 13. So I'm going to minimize this for just 1 second. So let's say we have this Venn diagram and we're asked for what the probability of B is here. Okay. If we go to our formula sheet, all right, we don't have this equation on there because it's really a combination of two things. So we know that the union of two events can be written out as the probability of both events minus their intersection. So if I look here on this Venn diagram, right, what's in both of these circles, right, this white circle kind of being event A, dark blue circle being event B, what's in both those circles would be the union of those two things. So if I take the area of both of these circles, right, what's in either one of them, and add that to this light blue shaded area, which I'm being told is the intersection of the complements, I know those two things have to add up to 1. So all I'm doing there is saying, I know that entire experimental outcome space is 1. Okay. So if I take the union, or what's in either one of those circles, and I add to that what's outside of those circles, which I'm told, and you'll be told on the exam this as well, is the intersection of the complements, I know those have to add up to 1. Now the trick is here, I know I had that equation on my formula sheet for the union, so I could rewrite this as the probability of A plus the probability of B, but then I have to subtract what I double counted or what was in both those events or the intersection. All right, so this is kind of rewriting the union using that formula from the formula sheet. I then add in, right, I still have this guy here. And now it's just simply plugging in what I know and then a little bit of algebra. So the probability of A is told to us to be 0.4. What we're looking for is the probability of B, so we don't know that. The intersection is 0.2, and the intersection of the complements is 0.1. Right? So 0.4 minus 0.2 is 0.2 plus 0.1, so I'll subtract 0.3 from both sides. I get, what, 0.7 is equal to the probability of B, okay? So the key there was knowing that what's in the area that's in either one of these circles represents the union of those two things, and that because this rectangle represents the entire experimental outcome space, we know the area of that rectangle has to be 1. Well, then the area that's in the circles plus the area outside the circles have to add up to 1. And like I said, the area outside the circles will always be told to you to be the intersection of the complements. So you don't have to worry about kind of remembering that. And then from there, it was rewriting the union of two events. Forgot my mouse today, so I'm using the mouse on my laptop, so I apologize if it's a little slower. The union of two events is just the probability of each event minus the intersection, okay? So that also kind of leads me to something we didn't talk about on Monday that could be helpful. So you could use that same thing using a contingency table. So I just want to mention this so you go back. We have a question like this on the second Excel assignment. So make sure you have a good understanding of that. I also know I worked through an example in class as well, where if we want to find the union of two events, if it's simply the probability of each event minus the intersection, well, I can get the probability of each event from the total columns. I can get the intersection from one of these top four left cells. So be prepared to be able to find the union of two events using a contingency table for the exam as well. If we have time at the end today, I'll work through one. If not, I'll make sure I work through one on Friday, but I wanted to mention that as some of you might be studying for the exam to know, make sure you know how to do that as well. Okay? So that takes us 10 through 15. We worked through 15 through, I believe, 17 last class. Right? So we've got a couple more that we need to do kind of here today. And I may not get through problems 1 to 4 today. We can save those for Friday, but those are some of the easier ones, so I just want to make sure I get the hard ones out of the way. So we had this example. I think this is where we actually left off on Monday's class. So we had approximately 64% of people have a visual impairment, and they need, glasses or contacts. So we found the expected number, right? We talked about that. Okay. And we're looking at 15 people. So we know that I think we have the expected number of people was 9.6. I'm sorry, I don't know why this is flashing. Hold on, let me see if I can get this to stop. Okay, there we go. I'm sorry about giving myself a seizure there. So if we want the probability that exactly 10 people have a visual impairment, we started out, we had n was equal to 15. The probability that any one person needed lenses was 0.64. Okay? And just as a reminder, when we calculated that mean, it was 9.6. So we know that the two most likely, if the mean is 9.6, what are going to be the most likely outcomes that we see? So we kind of said, the most likely outcomes will be the outcomes near the mean. And then as we move away from the mean, the probability will fall. Okay? So if we think about the probability that exactly 10 people out of these 15 have a visual impairment, well, if the mean was 9.6, 10 should have a fairly high probability. Okay? But we kind of want to explain this concept real quick. If we know that 9 and 10 are the most likely outcomes, right? It's not that one might be a little bit more likely than the other, but we know that they're going to be around the same probability, right? Because they're both kind of equally, right on either side of that mean. So if we think about which of these probabilities don't make sense, well, let's just assume for a second 9 and 10 were the only outcomes we could see, and that they were about equally as likely. Then they would both be around a probability of 0.5. So probabilities as high as 0.6 or 0.9 here don't really make any sense for this example, because I even just said, assume 9 and 10 are the only outcomes. Well, the highest, if they're equally as likely that it could both be, is 0.5, but they aren't the only two outcomes, right? We could see 0 through 15. So it's even less likely that the probability of 10 would be as high as 0.9 or 0.6. So if we're trying to just kind of take a guess here, B or C makes probably the most sense, okay? But we obviously don't just want to guess. So I go to my formula sheet, I scroll down here. I've got my binomial equations here for the mean, the variance, and then my probability mass function. So I'm just going to write out that probability mass function in the context of my example. So I've got n factorial over x factorial, right, times n minus x factorial, multiplied by the probability of success raised to the x power, and then 1 minus the probability of success, I'm going to run out of room maybe here, to the n minus x power. Right? Oh, wrong way. Okay. And at this point, it's a matter of getting comfortable using that factorial button in our calculator, making sure we can get this entered in correctly. Now, one thing I always mention is do the simple math first. Don't try to put this all in your calculator on one line. 15 minus 10 is 5. You know, maybe you could even do this in your head, right, is 0.36. 15 minus 10, this is 5. That way you eliminate needing to use as many parentheses, kind of making it a little bit easier to do in your calculator there, okay? Once again, if you're having difficulty finding that factorial button, please reach out to me. I had a couple people ask me on Monday, and we got it kind of taken care of pretty quickly, okay? I don't know why it's flashing again, sorry. Okay? I believe if we get this entered into our calculator correctly, we should get 0.209, right? So if we put this into our calculator, the probability that x is equal to 10 is that 0.209. Okay? Any questions on that before I keep moving here? Okay. So what if we keep running with this same setup? I'll actually leave this up here as I talk about the next one. But in problem 19, I want to know what's the probability that less than 14 people, so x should be less than 14. Well, if I think about anytime I want to find the probability of an event, I don't know why it keeps flashing. I think it's because I'm moving things around. So anytime I want to find the probability of an event, think about this as event A. I find every outcome that fits this criteria or that would belong to this event, and then find each of those outcomes probabilities and add them all up. Well, that's an issue, right? Because there's a lot of outcomes that fit this criteria, right? Let's see if I put this up on the screen, if I can get this to be a little bit less, get it to stop freaking out on me. Maybe if I turn the light off here. There we go. We'll kind of autofocus it. Oh, let's go a little bit darker there. There we go. That looks a little better, huh? So if I want to find this, I'd have to find the probability that x is equal to 13 plus the probability x is equal to 12 plus the probability. Well, each time I want to find one of those probabilities, I'm going to have to use this probability mass function, right? Well, that's going to be a pain, okay? So what's another way that I could find this? Well, if this is event A, I know that that's the same thing as 1 minus the probability of A complement. Well, if A is that x is less than 14, A complement is that it's greater than or equal to 14. Right? I then can think about, okay, what are the outcomes that fit this criteria that would belong to this event? Well, the very first one is that x could be equal to 14. Add to that, well, what's the next one? X could be equal to 15. But remember, that was our number of trials, so that's where it stops. Well, now we only have to use that binomial equation twice, right? And then subtract it from 1. That's a lot easier than finding, the probability x is equal to 0, plus the probability x is equal to 1, plus the probability x is equal to 2, plus 3, 4, 5, 6, 7, 8, 9, all the way up to 13, right? So using that complement rule kind of saves us a lot of time and makes this an actual, this problem a little bit easier, okay? Or actually just more realistic to have the time on an exam to complete, okay? So, we would go through, use this equation, but instead of x is equal to 10, we basically plug in 14s in for x. Then we would use it again, plug a bunch of 15s in for x. So I'm not going to write that completely out, but one thing I do want to point out, when you use that, when you're looking for x is equal to 15, I'll kind of write that one out for you. So we would have n factorial divided by x factorial times n minus x factorial times the probability of success to the x power times 1 minus the probability of success to the n minus x power. Well, remember, if we think about here, 15 minus 15 is 0. Anything to the 0 power is just 1. So if we're multiplying something by 1, doesn't change anything. We can essentially ignore that. Right? Here, 15 minus 15 is 0. Remember, 0 factorial, we said, is actually equal to 1. So this would just be 1, so we can really ignore that. Multiplying or dividing by 1 doesn't change anything. Then 15 over 15 factorial cancels. This whole thing is 1. We can essentially ignore that. All we're really left with, and we're finding that probability that x is equal to 15, is just that middle component. Okay? So that's just kind of reminding us of those rules, that anything to the 0 power is 1, and 0 factorial is also always 1. Okay? Any questions on that? Okay. I ran out of paper here. Let's make sure. Hopefully I have some other white paper. I thought I grabbed a ton, but I guess I've been going through it pretty quickly. All right, let me see. Gotta have something here that has white paper on it. Well, here we go. All right. That equals 0.209. Oh, could you, I missed that question earlier. So could you type in the bin equation for the last one on calculator?
Yeah, the equation for the binomial equation, I keep on getting the wrong answer. I don't get 0.209.
Oh, so how do we do this on Excel? Okay, give me 1 second. So I'm gonna go back to share screen. You're talking about problem 18?
Yes, yeah, 0.209, yep.
Okay, let me try this out. Don't look at those. They don't matter. All right, so we'll blow this up and make sure. This will probably help for the Excel assignment a little bit as well. But if you want to use that binomial distribution function, all right, so we wanted, was it 10 successes out of 15 trials, comma, the probability of success was 0.64, right? So we went number of successes that we wanted to find the probability of, number of trials, probability of success for any one trial. This last thing, because we're looking for the probability of exactly 10, we don't want it to be cumulative, so we'll put a 0 in there, or you could also use the word false, right? And that should give you the 0.209.
Sounds good.
That makes sense?
Yep.
Yeah. And it's easy to sometimes what I accidentally do, I don't know why. Sometimes I'll flip these, but it should just give you an error if you do that. I don't know. It's easy to kind of put the number of trials first. I don't know why I do that, but it's an easy mistake to make. Okay. All right. So last one that we'll kind of work through. This one should be relatively easy. We went through some examples on Friday, which I would suggest going kind of maybe looking back at, where we change the length of the interval. But this one, we're purely going to be focused on kind of just a regular Poisson distribution example. So we've got the number of people struck by lightning every year is 3. What's the probability less than 2 people are struck this year? Okay. So this one actually kind of combines quite a few different things. So we've got the probability that X is, oh, let me pull this up. And actually, we probably can just have the whole screen be this. So we wanted the probability that, was it less than 2? Now that I said we don't need that, of course, I forget exactly what we wanted. Less than 2 people, okay. So the probability that X is less than 2. Well, this is where we've got this event A. What's everything that would meet that criteria? Well, the very first outcome that meets this criteria is actually X is equal to 1, because there's no equality here. Okay? Then the next outcome we could see is X is equal to 0, and that's the lowest number of occurrences we could see. So we basically are going to have to use 2 probability mass functions. Okay? But which probability mass functions do we use? Right, well, if I go back, look at my formula sheet, I'm looking for the number of occurrences over a given time interval, so I'm going to use this Poisson distribution probability mass function down here. So it's got lambda to the x times e to the negative lambda divided by x factorial. Okay? So one thing I didn't identify here is we were told on average every year right? I believe it was 3 people are struck and killed by lightning, right? So we were given that right here, okay? So all I'm going to do is, and I'll actually, it might be helpful to have the formula sheet up as I work through this one. So there's our formula. So lambda to the x. So 3 is our lambda. The first x is 1 times e to the negative lambda divided by x factorial. And now for this probability, we have x is equal to 0. So lambda to the x times e to the negative lambda divided by x factorial. Okay. Kind of work this out here. So we've got what? 3 times e to the negative 3. So this should be about 0.149. And then e to the negative 3, 0.049. So we're talking approximately 0.199 if we round it to that third decimal. I can't remember what the answers were given to as. Yep, so 3 decimals, so 0.199. Okay. Any questions on that? So one thing if there's no questions on that Poisson one, one thing I wanted to mention I forgot to on the previous binomial, but it would apply to Poisson distribution examples as well. Sometimes don't get too lost in the formulas or too lost in some of this stuff. So if we go back to that previous one where we wanted the probability that less than 14 people had a visual impairment. Well, this is where we were saying, on average, we see 9.6, so the values of 9 and 10 are very likely. The values of 8 and 11 would be pretty likely, and then what would be 7 and 13. If we think about what's the probability that less than 14 people have a visual impairment, right? That's what we were looking for, and it was 1 minus the complement. Well, just think about, this is going to include all of the most likely outcomes, 9 and 10, which were really close to the mean, and then 8 and 11, which were the next closest, 7 and 13, and then all of the values below 7, right, 0 through 6. So this is going to include most of the outcomes, and it includes the most likely, right? The only outcomes it didn't include was 14 and 15, which are pretty far away from that mean. So right away, we should be thinking this is going to be pretty close to 1. If I'm going to guess on 19, I should have been guessing probably C or D. Right? Now, if I would have forgotten to subtract what I find here from 1, I'd probably find, I think it's 0.1 or 0.2 there, or 0.01 or 0.012. Let's look at the actual, so we didn't work that one out because it's really just kind of getting it entered into your calculator correctly. So it should, yeah, you'll find 0.012 when you add these up. And if you would have forgotten to subtract it from 1, then you might answer 0.012. But if you initially look at this and remember, oh yeah, I initially said this has to be really close to 1, the answer should be C or D. Oh, I forgot to subtract it from 1. Okay. Same kind of idea for this one, where we wanted the probability that fewer than 2 people are struck by lightning. Well, remember, the mean here was 3, so 3 is going to have the highest probability of occurring, and then 2 and 4 are going to be the next most likely outcomes that we see, and then from there maybe 1 and 5. But if we're thinking about probably that x is less than 2, well, it doesn't include some of the most likely outcomes, 2, 3, and 4, right? Given the mean that we're told. So finding having a probability as high as 0.85 there doesn't make any sense, right? That's pretty high for only finding the probability of 1 and 0 when those aren't even, that excludes the 3 values that are closest to or equal to the mean, right? 2, 3, and 4 there. So kind of just take a step back before you get into the formulas on these problems and just think about okay, given what the mean is, what should I be thinking about this probability is close to, right? This one's probably a little bit closer to 0 than it is 1. Sure enough, it's 0.2, right? Not as high as 0.8. Okay? Or, if I think about here, what if could it be 0.5? Well, if the probability that x was less than 2 is 0.5, right? That means that, these two outcomes would have had to be fairly likely, right? But we know that the probability of 3 has to be the highest, and that the probability of 2 and 4 are the next highest. So it doesn't really make sense that those would be as high, high enough to give us the answer of 0.5. If I'm guessing here, I'm probably guessing A or B. Once we work it out, sure enough, we get it's 0.199. Okay. Any questions on that one? All right, well, that's probably where I'll kind of stop for today. We'll review the very first 4 problems on Friday if anybody has any questions on them. They're pretty easy, and if we go back, I know it's old material, but finding things like variances, medians, and means should be fairly easy, I think, from a small data set like this. If someone's having some troubles with them, feel free to kind of bring those questions to class on Friday, and I'll kind of start with whatever questions anyone has. Okay? So I'm just going to end the video here for the one that I post, and we'll see you Friday.